Hi and welcome to this week's lesson from TheMathsTutor.ie for Leaving Cert Ordinary Level Maths. So this week we're going to be continuing looking at geometry, and this week we're going to look at the geometry of circles. As always, there's loads of resources available on TheMathsTutor.ie for all the full members, and we make some of those resources available each week for the people tuning in for these lessons. So this week's videos to watch after this lesson, the first one there is on something called cyclic quadrilaterals. And the second one is on circles and chords, and it's going to explain a little bit about something we're going to see about our circles and our chords in this lesson. So before we can start looking at some exam questions, we just need to do a little bit of going over what we mean by our circle and what we mean by the geometry of a circle. So this diagram here is of a circle, and it's a circle because it has a center marked here in black. And the distance from the center to every point on this blue circle here is going to be exactly the same distance. And we call that distance a radius. So we've one radius marked in here, the distance from the center down to this line, and that's going to be the radius. This red line here is not a radius, this is a chord. So a chord goes from one side of a circle to the other. So that's a chord there going from one side of the circle to the other. If we have a chord that goes through this center point, so if it starts at one side of the circle, goes through the center and goes right to the other side of the circle, that's a special type of chord called a diameter. And the length of the diameter will always be twice the length of the radius. So if I know the radius, I can find the diameter, and if I know the diameter, I can find the radius. There are two right angles marked in this diagram here. So we have a right angle here and a right angle here. And both of these right angles are important when we're looking at our theorems to do with our circles. So the first right angle that we have here is alongside this chord and this green line that's coming from the chord to the center. Now this isn't a radius because it only goes from the center to the chord. It doesn't go as far as the edge of the circle. So this distance here is called a perpendicular because it makes a right angle with this chord and it's coming from the center. And when we have a perpendicular from a center to a chord, our theorem tells us that the chord is bisected. So that means that distance there is equal to that distance there. So we divide the chord exactly in half whenever we have a perpendicular coming from the center. We also have another perpendicular coming from the center here. So this green one here, this radius that we've talked about, goes right to the edge of the circle and it forms a right angle here. And it's forming a right angle with this line down here. Now this line is not a chord because it's not crossing the circle twice. It's not going from one side of the circle to the other. This is touching the circle at this point here. And when we have a line that just touches a circle like that, we call it a tangent. And we call this point here the point of tangency. And the radius that comes from the center to that point of tangency is always going to form a 90-degree angle with that tangent. So we're going to see that is going to help us to solve working out some of our angles in our circles from the questions from the papers shortly. There's another theorem that we need to look at before we can look at that. And here we have two circles with the center marked in black. So this is the center of this circle and this is the center of this circle. So in this first circle here on the left, I can see that I have points on the circle down here. And from these points, we're forming an angle, one of them up here at the circle. So I would describe this angle as being at the circle. And one angle that's being formed at the center. So this angle here is at the center. And once these two angles, the angle at the circle and the angle at the center, start from the same 2 points, then I can say that the angle at the center is going to be double the angle that's at the circle. So we describe this as being angles at the circle and angles at the center formed from standing on the same arc. So this part of the circle here, between these two black dots, is called an arc. And once we start with the same arc, So I'm starting at one part of the arc, going up to the circle and back down to the other part of the arc. This angle at the circle is going to be half the angle that's formed when I start that arc and go to the center and back down to the other end of that arc. And that gives us a very important part of a theorem that we use quite a lot when we're solving our triangles. And that's when our arc is going to be formed from the two end points of a diameter. So here we see this special chord. It's going from one side of the circle to the other, but it's going through the center point. So that makes it a diameter. But we still have an angle being formed at the center and an angle being formed at the circle. So the angle that's formed at the circle starts at this end of the arc. It goes up here to the top of the circle and it comes down to the other end of the arc. So this is at the circle. And what I mean by that is it's on this blue part here, this blue circle that we've drawn. So it's the angle that's formed where they meet at the top. And this angle here is at the center. Now the angle that's formed here at the center, I can see that's a straight line. So that's going to be 180 degrees. So my diameter is a straight line. So when I have this chord going through the center, my diameter is going to form 180 degrees at the center, which means that the angle at the circle is going to be half of that measurement. So if this angle at the center is 180 degrees, the angle that's at the circle up here is going to be a 90-degree angle. And we often refer to this as the angle in a semicircle. And the reason that we describe it as being in a semicircle is if I take the line from this diameter and go around to the top, we get half of the circle. So that's a semicircle. So you'll often hear people refer to the angle in a semicircle is 90 degrees. And it comes from this theorem that the angle at the center is going to be twice the angle at the circle. So now that we know those few things about circles, we're going to have a look at a couple of questions from the papers and see can we apply those pieces of information. So we're going to start with 2019 paper 2 question 6b, and this says in the diagram O is the center of the circle S. So this is going to be the center of my circle. And that means that we have a line that starts at W and goes to X. We have a special chord here, so it's going from one side to the other, and that means that that's going to be a diameter. So we have a diameter from W to X. So the line segment from W to X is equal to the diameter because it's a chord going from one side to the other and it goes through the center. So the question then says find the value of alpha, so that's our little a up here, and beta, which is our b down here. But down here we just need to keep an eye to make sure that you note that this says 2 beta. It's not just beta on its own. So with this, we're going to have a look at our triangles that are formed in this circle and see can we answer this question using our circle geometry, and we might have to use some of our other geometry that we've come across already as well. And why I say that is when I look at this first, I see there's a line drawn here from O to Y, and it's coming from the center to the circle, so that's going to be a radius. And we know that W to X is a diameter, and that the diameter is twice the radius, so that means the distance from W to O is also a radius. So when I look at the triangle that starts at W to O to Y and back to W, I have a triangle with two sides of the same length. So that means I have an isosceles triangle. So I'm going to say the triangle WOY is an isosceles triangle. So isosceles triangles have two sides the same, and when they have two sides the same, they also have two angles the same. And the two angles that are the same are the two that are at the base of the sides that are at the same, so not where they meet. The two angles at the base are going to be of the same size, so that means that alpha is equal to 52 degrees. So from spotting our isosceles triangle here, we're able to work out that we have a 52-degree angle at alpha. So then we're going to look and see can we calculate the size of the angle 2 beta. And to do this, I'm going to go back to looking at my diameter. So here's my diameter, and we're going to use that theorem that we had about the angle at the circle is half the angle at the centre, and when we have a diameter, the angle that's formed here at O is going to be 180 degrees. So this full angle here is 90 degrees. So that means the size of the angle from W to Y to X is equal to 90 degrees. So when I look at this green triangle, I now know two of the angles in this triangle. I know that the size of the angle from W to Y to X is equal to 90 degrees because it's an angle in a semicircle. And when I add the 90 degrees to the 52 degrees, 90 degrees to 52 degrees, I'm going to get 142 degrees. And the three angles in a triangle always add up to 180 degrees. So I know the angle at W, the angle at Y, and the angle at X are going to add up to give me 180 degrees. So I can say 180 degrees, take away the 142 degrees, and that leaves me with my third angle in this triangle being 38 degrees. So this angle here, I've now calculated, is going to be 38 degrees. But we just have to remember that this was the angle 2 beta. So if 2 beta is equal to 38 degrees, I'm going to divide by 2 to get beta on its own. So that gives me that beta is equal to 19 degrees. So we used our theorems about our circles, but we also used some theorems there about our triangles. So we spotted an isosceles triangle and we're able to work out that two angles were the same. And then when we used our circle theorem to work out that this angle up here was 90 degrees, we went back to our theorem about triangles and the three angles in a triangle summing to 180 degrees to work out our third angle. Okay, so the next question we're going to look at then is 2010, and this is paper 2, question 9b, part C. So this is just one part of a long question, and there isn't a lot of space given for this for working out. So it says in the diagram, the line L is a tangent to the circle. So I'm going to highlight this. This is a tangent to the circle, and then I want to find the values of X, Y, and Z. So if we have a tangent to a circle, I know that at the point of tangency, which is here, the radius that comes from the center and touches the tangent at the point of tangency is going to form a right angle. So I can see that this angle here is going to be a right angle. So Y plus Z are going to equal 90 degrees. So I'm going to make a note of that. I don't have enough information to solve that yet because there's two unknowns and I only have one equation, but we're going to see can we solve anything else in the triangle. Because this is the center of the circle here, we have our point of tangency. That means that this is our diameter. So this line here is our diameter. So again, we have one of these triangles in a semicircle, and this is going to be 180 degrees at the center, which means that the angle that's formed up here at the circle is going to be 90 degrees. So I can write down that X is 90 degrees, and I'm going to give my reason for it. So it's the angle in a semicircle. So now that I know that this is 90 degrees, when I look at the triangle that's inside this circle here, I can see that I now know two of the angles, 42 degrees here and 90 degrees here, and that means I'm going to be able to work out my third angle. So we're doing this the same as in the last question. We're going to take the two angles that we know, we're going to add them together and we'll subtract them from 180, and that'll give me my third angle. So I'm going to say 90 degrees plus 42 degrees, which gives me 132 degrees, and I'm going to subtract that from 180, and that gives me that the size of that angle is 48 degrees. So the angle at Y is 48 degrees, and I used the fact that the three angles in a triangle sum up to 180 to calculate the size of that angle. And now that I know that Y is equal to 48 degrees, I can substitute that into this original equation that we came up with our point of tangency. So that means that 48 degrees plus Z degrees is equal to 90 degrees. So if we subtract 48 from both sides, we're going to calculate the value of Z to be 42 degrees. So I'll fill in my answer here for Z is 42 degrees. So we had a couple of different things that we had to use there. So we used the fact that at the point of tangency, the distance or the radius that comes from the center here will form a 90-degree angle. So y plus z are going to add to give us 90 degrees. And because this was a diameter here, that meant that the angle that was formed up here at the circle was going to be half the angle that was formed at the center. So the angle at the center is 180 because it's a straight line. So the angle that's formed up here at the circle is going to be 90 degrees. And once we know two angles in a triangle, we can add them together and subtract from 180 to find the third, because the three angles in a triangle add up to 180 degrees. And that allowed us to then substitute and solve for Z. And we're going to be using something similar in the next question. So this is 2014 paper 2 question 6b, which says two circles C1 and C2 intersect at the points B and X as shown. The circle C1 has a diameter of AB. So the distance that's running from A to B is the special chord that goes through the center. So the center is somewhere around here. And the circle C2 has the diameter from BC. So the line segment that goes from BC is a special chord as well. So the center is going to be somewhere around here. And what we're asked, and the last thing we need to be given here is the line CB is a tangent to C1. So this line segment here from CB is going to form a tangent to this first circle C1. And that's important because it's going to give us an angle up there, which we may need to use our 90-degree angle. So what we're being asked to prove is that X is on the line AC. So we don't have a line segment drawn in from AC yet. So we're going to draw in roughly one from A to C here. Okay, so it's a little bit off. Okay, sorry, we'll just erase that one. And just do a little bit neater if we can from A to C. Okay. So that's a little bit better there. So we have our line segment now running from A to C. And what we want to prove is that X is on this line segment. Okay, so to do this, there's a couple of things that we're being told. And if we're being told information, we're going to try and use that if we can. So I was told that the circle C1 has a diameter running from A to B. So that means that the angle that's formed here is 180 degrees. So the angle that would be formed at the circle would be 90 degrees. But I don't have an angle drawn in for me at the circle yet. So what I'm going to do is I'm going to draw a line that joins B to X. And when I draw this line that joins B to X, I can see that X is on both of these circles. So I can see that it's on both of these circles. Now, it hasn't proved that it's on the straight line from A to C yet, but the fact that it's on this line that joins B to X here, and the fact that this angle here was 180 degrees, means the angle that's formed up here at X is going to be 90 degrees. So that's our angle in our semicircle. Here in the circle C1, the distance from A to B is the diameter, so we form 180 degrees here, so we're going to have a 90 degree at X. The same with BC, so BC is a diameter as well, so that means we also have 180 degrees at the center of this circle, C2, and because of that, it means that we'll have a 90 degree angle here, formed from the angle in a semicircle. So because we now have two angles at X that are going to add up to give me 180 degrees, that means that the line AXC is going to be a straight line, and it proves that X is on that line. So we're going to just write that down. So we're going to say the size of the angle from B to X to A is equal to 90 degrees, and the size of the angle from B to X to C is equal to 90 degrees. And the reason for both of those is because they're the angle in a semicircle. So we had to draw in those angles to make them see this semicircle, but we can prove that we do have that 90 degrees in that semicircle. The angle at the circle will always be half the angle that's formed at the center. And now, because both of those are 90 degrees, when we add them together, we're going to get 180 degrees, which is a straight line. So when two angles add up to 180 degrees, that means those two angles have to form a straight line. So that means the size of the angle from A to X to C is equal to 180 degrees. So it's a straight line. And because it's a straight line, that means that x is on the line AC. Now, another way that we can describe that and another term that we can use is the word collinear. So we can say A, X, and C are collinear. And collinear just means points on the same line. So it could have been worded, instead of saying show that x is on the line AC or prove that x is on the line AC, it could have asked you to prove that A, X and C are collinear, and we would do exactly the same thing. Okay, so that's using our tangents and using our angles in a semicircle. The next question we're going to look at has a slightly different twist to it. And this is 2011 paper 2 question 6b. So this says, in the diagram, ABCD is a cyclic quadrilateral and ABCF is a parallelogram. Show that DEF is a cyclic quadrilateral. Okay, so we've already looked at our parallelograms, and we know that in a parallelogram, opposite angles are equal and opposite sides are equal and opposite sides are parallel. But we're coming across a different term in this question, which talks about cyclic quadrilaterals. Now, one of the videos to watch after this lesson is about cyclic quadrilaterals, and it'll go into those in a little bit more detail. But what we need to look at here is we need to understand what this term means before we can prove this question or before we can answer this question, because this term cyclic quadrilateral is mentioned twice. So the first thing we're going to look at is a quadrilateral. So a quadrilateral is a four-sided figure. So we have lots of special quadrilaterals like a trapezium, a square, a rectangle, a parallelogram, a rhombus. There's lots and lots of different types of four-sided figures. The one that we're coming across here is a cyclic quadrilateral. And a cyclic quadrilateral is formed when we have a four-sided figure so that means it's a quadrilateral, that a circle can be drawn through. The four corners. So it tells me that ABCD is a cyclic quadrilateral. So I'm looking at the shape that starts at A, goes to B, goes to C, goes to D, and goes back to A. So I can see that this is my four-sided figure here with my straight sides, and I can see that that makes it a quadrilateral. It doesn't look like a square or a rectangle or a parallelogram, but it is this special type of quadrilateral called a cyclic quadrilateral. So I can see that this dashed line that they've drawn in here goes through the point A, through the point B, through the point C, through the point D, and back to the point A. So we're able to draw a circle through the four corners or the four vertices of this quadrilateral, and that makes this a cyclic quadrilateral. Not all quadrilaterals are able to be cyclic quadrilaterals, so we can't always draw circles through the four corners of a quadrilateral, only when they have certain qualities. And the most important thing about this is, in a cyclic quadrilateral, opposite angles sum to 180 degrees. So that's a really important quality about cyclical quadrilaterals, is that opposite angles are going to sum to give us 180 degrees. So when I look at this cyclic quadrilateral, I can see that the size of the angle from B to A to D plus the size of the angle from B to C to D are going to add up to give 180 degrees. So this angle and this angle are going to sum to give 180 degrees. And I can also see that the size of the angle from A to B to C plus the size of the angle from A to D to C are also going to sum to give 180 degrees. So there, from my cyclic quadrilateral, that's the important piece of information that I have figured out. So that's using the fact that they told me that this was a cyclic quadrilateral. We're also told that ABCF is a parallelogram. So starting at A, going to B, over to C, and back up to F and back to A is going to be a parallelogram. And one of the things we know about parallelograms is that opposite angles are equal in measure. So the angle from B to A to F is going to equal the angle from B to C to F, and the angle from A to B to C is going to equal the angle from A to F to C. So some of that might be important to me, because what I want to show is that the quadrilateral DEFG is a cyclic quadrilateral. So from D to E to F to G and back to D, I can see that it's definitely a quadrilateral. It's a four-sided figure, and I'm trying to prove that there is a circle that will go through the four corners or the four vertices of this quadrilateral and form this circle. So how I'm going to prove this is I want to show that opposite angles sum to 180 degrees. So we're going to have to use some information that we know about angles already. So what we've mentioned already is that the angle here from A to B to C, so the angle from A to B to C, is equal to the angle that's here from G to F to E. And why they're equal is because they're opposite angles in a parallelogram. Another thing that I can see is that the angle that's formed here, so the angle from A to D to C, is equal to the angle that's formed here, which is the angle from G to D to E. And why they're equal is because they're vertically opposite angles. So we talked about vertically opposite angles being equal in measure. The last thing that we're going to need to prove here is that we've already mentioned that when we add the angle from A to B to C to the angle from A to D to C, we know that they add up to give 180 degrees. And they add up to give 180 degrees because they're opposite angles in a cyclic quadrilateral. So the size of the angle from A to B to C plus the size of the angle from A to D to C, size of the angle from A to D to C, are equal to 180 degrees because they're opposite angles in a cyclic quadrilateral. But we've said that these two angles match, and we've said that these two angles match, and then we've said that these two angles add up to give 180 degrees. So that means that these two angles here are also going to add up to give 180 degrees. So we can say, so the size of the angle from G to D to E plus the size of the angle from G to F to E are also going to equal 180 degrees. So that means that these two angles here have to equal 180 degrees when added. And in a quadrilateral, all the angles add up to 360 degrees. So if these two add to 180 degrees, it means that these two also have to add to 180 degrees. So by proving that in a quadrilateral, these opposite angles sum to 180 degrees, that means that DEFG is also a cyclic quadrilateral. So one of the videos we're making available this week is a little bit more information on our cyclic quadrilaterals, so you might want to look back over that. And the other video that's there available for you is on your circles and your chords. So it proves that fact that when we have a perpendicular from the center to a chord, it's going to bisect that chord. So hopefully this lesson on geometry of circles has been useful to you. Thank you very much.